Hello, my name is Eric Newman. I'm an applications engineer in Keysight's PathWave software organization. Today I'd like to show you how you can use Genesys and SystemVue Sys-Parameters within the ADS environment. This allows system engineers and ADS circuit designers to share the same behavioral models across the various platforms. For those that aren't familiar with Sys-Parameters, I'd highly encourage going and doing a search on the internet for Keysight Sys-Parameters, and several videos will be available to give you some background. To start off, I'm in our SystemVue tool here, and we're just using the basic start page, an RF architecture template here to get started. It just consists of a source, an ideal amplifier, and an output termination. In this case, we're going to use a part from Custom MMIC. We're going to be designing a portion of a 28 gigahertz transmitter today. So I'm just going to scroll down and peruse the different parts and find a driver amplifier. That would be appropriate. Drop this part into the schematic, run our simulation. And what we'll see is within the workspace tree, this data folder has been populated. And within it, you can see there's frequency dependence, gain, noise figure, output IP3, output P1 dB. This part you can see has actually been optimized up around the 28 gigahertz band, providing high output linearity up at these frequencies and low noise and moderate gain up at 28 gigahertz. But anyways, what we want to do is try to get these parameters, this kind of model, into the advanced design system. So first, I'm going to go ahead and right-click on the component and look at the Sys-Parameter spreadsheet. So this is a comma separated value spreadsheet. We can easily open it up in Excel, and we can look to see what's in here. You can see there's a few columns: independent variable frequency, gain, noise figure, P1 dB, reverse isolation, output IP3, and output PSAT, saturated output power. Okay, so what we want to do is we're going to reformat this file so that it can be easily digested into the advanced design system. So first thing I'll do is just Control A, pick all that data up, Control C. I'm going to go to a new page here, paste this in. Okay, now that we have this data pasted into a new sheet here, we'll make a few modifications. The exclamation point will be recognized as a delimiter to comment away the information on that row. On the second row, we're going to type begin, and we'll call this block data. That tells the tool that the next relevant rows of data will be the data that we're trying to take into the multidimensional interchangeable format, file format that we're going to use in the advanced design system. So we have the test conditions are commented out already. We're going to make a few modifications to this row here, which includes the independent variable and the dependent variables. We're going to add a % before the independent variable. That delimiter will let the tool know that this first named column here is going to be the independent variable. We're going to make another change. We're going to call it freak in. The word freak is a reserved variable in the advanced design system, and to avoid simulator conflicts, we will change that name to freak in. We will add parentheses real directly after the variable to indicate that that data is real. We could also use complex and other formats as well. We'll make additional changes here. The column for gain, we're going to do the same, add the real. Noise figure, we don't want to have two separate words there. That won't be interpreted as one variable. So we'll make it NF here. Add the real syntax here to indicate it's a real format. We'll carry on. We'll do the same for the other parameters that we want to use in our simulation. We'll pull all these guys in. Real. Output saturated power. Real. Okay. Next, we're going to change the frequency range here to use hertz rather than megahertz. This is again to avoid simulator conflicts later. We're going to add that exclamation point now to this row so that the simulator doesn't try to read these units in. But I do like to change the units here to make sure people realize that this is actually in hertz now after we make the modification here. We're going to go ahead and change this column to equal the frequency on the first page, and we will multiply that times 1 e to the 6 to get it into the units of hertz. And we'll copy and we'll paste, convert that column. There. Now one final step, we need to add an end statement here. Okay, these are the essential things to read in one block of data into a generalized multi-dimensional interchangeable format, file format in the Advanced Design System. So here I'm just going to go ahead, select the modified sheet here, Control C, and then just go to a simple WordPad editor. Okay, now with WordPad open, go ahead and do a paste special. I'm going to go ahead and say paste special, unformatted text. Click OK. You can browse the data. You'll notice that there was some wraparound here on the individual rows. Don't worry about that. The tool will know that there is one independent variable and 1, 2, 3, 4, 5, 6 dependent rows of data. And so it'll parse the data accordingly from this set. So I'm going to go ahead and say File, Save As, and we'll save it as just a text document here. I'm going to give it a name, CMD243, and hit Save. I think I should save this over in my temp folder here. Yes, sure. Okay, so now that I've saved that away, I can go to that folder location on my computer. Bring that over into the window here. And I'm going to make one other edit. I'm going to go ahead and say rename. And I'm going to change actually the extension to be an MDF. Oops, lowercase, sorry. So now we'll get ready to use this in our ADS project. Okay, I already have my ADS workspace open, and I've opened up the cell 04, single data access component, test bench with frequency sweep. So let's talk a little bit about what's inside this example here. First, let's open the data access component. Data access component allows us to point to our MDIF file that we just created. We can open and edit that MDIF file if we want to check its contents. This is the previous data we had open earlier. Again, just shown in WordPad here as a default editor. And we need to make sure that we have the file type, in this case, set for generic MDIF. There's an independent variable is defined over in this tab here. Freak_in is our independent variable, and it has a value of freak_in. So we've added that in here. And then there's interpolation that can be used. In this case, we're using rectangular data. If you had a polar format, you might want to use the polar format, and that allows the tool to properly interpolate between points. And then the extrapolation method we have set for constant extrapolation. So the data access component is pointing towards the MDIF file. So then we use some equations over here. These equations are file-based. We're using a file-based entry mode so that we can select the data that is available to the data access component. In this case, we're showing the noise figure. In this case, we're showing the gain. In this case, we're showing the output PSAT. So this variable to block allows us to get that data from the MDIF and then use those variable names to define within this amplifier to block what is the S21, the gain, what is the reverse isolation, what is the noise figure. So all these have been entered in here already. We have a harmonic balance simulation controller. We again have set the frequency for freak_in here. We're doing a 5th order harmonic balance simulation. We're not doing a sweep here. We're actually doing the sweep over here from the parameter sweep block. We'll come back to that in a moment. We do have noise enabled. So if you open up these noise tabs, you'll see that there's a freak_in as the noise frequency and input frequency is noise frequency. This allows the harmonic balance simulation to give you the noise figure after you simulate. The parameter sweep, again, that's actually doing the simulation of the harmonic balance simulation, in this case, and we're sweeping f-start to f-stop. We've also added a large signal S-parameter simulation controller here as well, evaluating at freq in. Similarly, we have to set input ports, freq in for port 1, freq in for port 2. There's no frequency translation in this example. So now we have all our variables set up. We can click Simulate. If everything goes well, we should get a nice little plot that we can verify the performance of the device. We can see the S12, the reverse isolation. We're simulating from 20 to 40 gigahertz. We can see the S21 large signal, S21 for the device. We can also plot our power out. In this case, we have a 0 dBm input signal, so we should get a curve that looks very similar to the gain curve here, as long as we're not compressing the amplifier. In this case, we are not. And we also have the noise figure plotted out for us available. So now we've been able to verify that our component model is working. Okay, now we've verified that the basic model is working. Let's have some fun. I've also included in this archive an example of a 5G verification test bench. And we've simply gone ahead and taken the data access component, the variable blocks, and the amplifier model from the previous cell and copy and pasted them into this cell and added a 5G filter bank multi-carrier verification test bench, and allowed the verification test bench to generate the envelope controller for us to run the simulation. And we also added a measurement equation to pass the node voltages over into the data display for post-processing. So we can click Simulate on this design now. Okay, looks like the simulation is completed. So now after the simulation completes, the data display already opens for us. It gives us several bits of information. We can look at the CCDF, the spectrum, the peak envelope of the waveform versus time, or index in this case, actually. We also have a few other bits of information as well. We're getting the EVM after the dot and before the dot. So we can see in this case our EVM is getting degraded at this power level. We're feeding a 0 dBm power level in. Data display here calculates as 0.2 in this case, as well as we have information such as the peak to average ratio. We have the mean power and the peak power before and after the dot. We can use a simple equation and we can calculate what's the peak to average ratio, how much gain are we seeing here. At this frequency, we know we should have a little bit more gain than we see here. So we do have some compression issues, and we can tell from the peak to average ratio as well. It's normally a bit higher for this waveform. So we'll go back to the schematic now, and we can go ahead and change our power levels here very easily. Just go ahead and enter in here and go down to minus 20 dBm. We'll back it off a bit and run the simulation again. Okay, so the simulation is finished. It took almost a minute to run this simulation. But now we can come back, look at the data display again. We can look at the output waveform, input waveform spectrum, and see that we're not generating as much power in the sidebands here of the waveform. The ACPR is being fairly well preserved. We can look at the EVM again. Now we're 51 dB EVM. That's quite a bit better than what was before. It's definitely acceptable for this waveform. And we come back and verify we're seeing our 16.3 dB gain here because we're not compressing, and we have about 11 dB peak to average ratio, which is what we expect for this waveform. Okay, so I hope you found the video useful. If you'd like to understand more about how to use MDIFs and data access components within the ADS platform, I'd highly encourage you, if you're not already, become a member of our Keysight Knowledge Center, and you can have access to these documents. In this case, I'll just search for sourcing MDIF, and we can find many references that are useful here to help understand how we can use MDIFs in ADS with the data access component to make use of that general data. I highly recommend if somebody wants to get into a lot of detail here, I think this is a wonderful app note here about sourcing generic ASCII data into ADS simulation. It provides several examples. Most of our Knowledge Center examples will have examples potentially at the end as well to give you more to understand and study. So I hope that was helpful to you and you enjoyed this video. Thank you for your time.